then I'm going to start sharing my screen. You see the screen there, right? And then I need to turn this, start sharing my screen. Yeah, I have to mute the, because I'm monitoring both. So most of the time I pay not so much attention because I'm monitoring all these things all the time. So unfortunately, I'm the one that has to watch the talks afterwards, yeah. But that's okay. That's the way it works. That's the way it goes. That's wait until it becomes. People usually comment directly at the time when things start. Okay, slowly will show up. I think they all know that I start and it might usually spiel. Okay, so let me begin maybe. So thank you everybody for the new another online SPICE-SPIN+X seminar. As you know, this is led by the Spin Phenomenon Interdisciplinary Center that I lead together with Carrier-mediated and in collaboration with a collaborative center, SPIN+X, between Kaiserslautern and Mainz, led by Martina Schliemann, Burkhard Hillebrands, and Matthias Chloe. The talks are webinar format, meaning that you will hear the talk and the speaker, and then you can ask questions and write your questions, please, on the Q&A. And after the talk is over, I will give you the microphone to be able to ask questions directly to the speaker. If you don't have a microphone, just let me know, and I will ask those questions directly to the speaker. In this case, to Tomasz Dietl. So Tomasz Dietl is a very well-known person in our field of spintronics. He's the father of magnetic semiconductors. He's now head on professor of the International Center of Interfacing Magnetism and Superconductivity with Topological Matter, called MACTOP, a very successful program in the Institute of Physics of the Polish Academy of Sciences. He's developed over the years many things on topological insulators for magnetic and antiferromagnetic semiconductors, one of the most impactful of his work in this area, and has a very large list of honors, such as the Maria Slokowska-Curie Award in Poland, but also the Alexander von Humboldt Research Award, etc. And today he has the floor. So let me stop sharing here, and I'll ask Tomasz, please go ahead and share your screen and begin your talk whenever you can.
Okay, is it okay with the scene?
Yeah.
Many thanks, Jairo, and many thanks to Karin, Matthias, Martin, and Burkhard for organizing this wonderful series of seminars, which many of us enjoy very much, and for this kind invitation to be one of the speakers here. And today, actually, I have two goals. First, I will recall you many notions which actually concern dilute magnetic materials. It will be based on a paper article chapter we contributed to Handbook of Magnetic Materials, which hopefully will be printed or will be online next year. And in the first part, this will be kind of a long introductory of the systems. And then in the second part, I will be more specific. I will speak about applying electric field to the system. What happens if we have electric field acting on this dilute magnetic materials? Well, there are many issues, of course, and the first which make different between dilute materials or not dilute material is that we have a very important question which we have to ask at the beginning about distribution of this magnetic component. Very often we assume that it's random, but it turns out that actually in many cases, it's very far from being random. It's actually a very correlated distribution. And in many cases, you have actually very nice patterns which results from this aggregation of magnetic impurities. And for instance, what you see here is germanium manganese. If you make X-ray, you would see that you have beautiful diamond-like structure. But actually, if you make chemical investigation, you see that manganese is not randomly distributed, but forms beautiful nanocolumns along the growth direction. The same you can observe in the case of zinc chromium telluride. This time, this nanocolumns grows along 1-1-1 direction. And we call this phenomenon spinodal decomposition, that again, we have beautiful zinc blende structure here, but locally, using chemistry, we see that there is aggregation of chromium atoms in the form of nanocolumns. Of course, you can have many different shapes, and you can ask the question, I think, a relevant question, when and to what extent the self-organized growth of magnetic nanostructure will be competitive with top-down approaches dominating today. So probably at some point it concerns spintronics, but it also may concern electronics, that we dream about self-organization instead of top-down methods which are dominating today. And another notion associated with spinal decomposition, which I think is relevant beyond dilute magnetic semiconductors, it's anisotropic spinal decomposition. What you see here is just indium arsenide doped with iron. And you look again for crystal structure, you see a very well arranged zinc blende structure, but if you have chemical sensitivity, you see that actually iron arsenide forms nanoplates perpendicular to which grow along the growth direction and are oriented about 1-1 O direction. So there is kind of anisotropic spinodal decomposition. One of the axes is preferred by this arrangement of these nanoplates comparing to other. We call this effect nematicity, and this effect leads to breaking of rotation symmetry. Instead of D to D symmetry, we have C to V symmetry. So we have lowering of symmetry with all consequences. For instance, if we study AMR or other phenomena, you clearly see that symmetry is lower. And actually, this is observed in many systems. For instance, if you study quantum Hall effect or fractional quantum Hall effect, the very standard gallium arsenide, aluminum gallium arsenide, you also see this breaking of symmetry, rotational symmetry. In gallium manganese arsenide, we are very well aware about this symmetry breaking. And for instance, superconductors, if you study anisotropy of GAPU, you also see this very clear lowering of crystal symmetry. And if you go to literature, you find that in most cases, people believe that we deal with spontaneous symmetry breaking, for instance, by ordering of charge or spin or orbital degree of freedom at low temperature. So what people try to explain many of these effects, that at lowering temperature, at some point there is spontaneous symmetry breaking, and we have, for instance, orbital of charge order. What our results suggest, and we see there are more arguments towards that in most cases, not in all, but in most cases, symmetry breaking, this nematicity, which people discuss, originate from quench anisotropic spinodal decomposition of alloy components, impurities, defects, which appears during the growth, not due to spontaneous formation of this many-body phase, for instance, due to charge ordering. So one should be very careful, and physical, you can ask about physics, what causes this anisotropic spinodal decomposition. And physics is associated, as we discussed with the theoretical paper, and demonstrate that physics is associated with the fact that growth surface has usually lower symmetries at bulk, and this quench anisotropic spinodal decomposition actually begins during growth at the growth surface, which, as I said, is lower symmetries at the bulk of the system. Then you see in bulk also this pattern, which is at the surface. Okay, but in some cases, actually, we can manage to have random distribution. And first, I will start discussing situation where we have magnetic ions, randomly distributed as a lattice, but no carriers. So we can ask about spin-spin interaction. And I think everybody is well aware about the fact that in that case, we have super exchange. We know this for half-edge junction, that in such a cases with no carriers, in compounds, we have indirect coupling through anions, which could be always, which actually is always present in magnetic compounds. If you are interested in a theoretical description, we know that it's related to this PD coupling between D wave function and ion P wave function, short range, usually it is antiferromagnetic. And in case of tetrahedral coordination, it's antiferromagnetic for manganese 2+, if we have 5 electrons, if we have cobalt 7 electrons, and so on. But it can be in some cases ferromagnetic. And this is the case of manganese 3+, chromium 2+, vanadium 2+. In case of tetrahedral DMS, it would be different in the case of octahedral situation. And let's start from this antiferromagnetic interaction as an example. Of course, there are plenty in literature. What we study here is zinc cobalt oxide, a material which many people have been studying. Many groups were interested in this material for various reasons. And what you see here is inverse susceptibility plotted as a function of temperature. And you see immediately that interaction must be antiferromagnetic because Curie-Weiss temperature is negative. And you see that common intersection of this curve occurs. And if you think a while on Curie-Weiss temperature, Curie-Weiss constant, Curie constant should be proportional to magnetic ion concentration. In a random system, Curie-Weiss temperature is also proportional to, in high temperature expansion, to ion concentration. So at 0 temperatures, this X dependence cancel. And actually this crossing of these lines in one point demonstrate very beautifully that we have random distribution. If you would have correlated distribution, we will not observe such crossing. So we have random distribution. We see also that down to very low temperature, actually, we do not see too much ordering. And also, one of the reasons people were so much interested in this material is that under a specific growth condition, you can observe ferromagnetism. And nowadays, we know, I think, most of people agree, there are cobalt inclusions which account for this ferromagnetism, or this is more fancy and less popular, that uncompensated spin at surface of antiferromagnetic cobalt oxide nanocrystal are involved here. And to give you an idea about energy involved, theta, Curie-Weiss temperature extrapolated to 100% of cobalt is of the order 700. So it's large energy, and actually this large energy of interaction can make that at room temperature still we have uncompensated spins at the surface which are ordered by antiferromagnetic interactions surviving up to room temperature. And I already said that we have no ordering despite the strong coupling. And here is another notion which is important in many systems, but also in random antiferromagnets, is frustration. So we have very strong interaction, antiferromagnetic interaction between spins, but spins are frustrated, and actually we do not observe antiferromagnetic ordering because of this frustration. What do we observe? It is known that random antiferromagnets order and have spin glass freezing at low temperature. And this temperature freezing depends on concentration, but for instance, 16K for 42% of the cobalt. So it's relatively low temperatures. This freezing temperatures might lower that Curie-Weiss temperature because of this frustration present on the system. So now we turn to another material. Now we turn to gallium manganese nitride. It's another example of dilute magnetic semiconductors where there is not too much carriers. And actually, people were looking for this material for a reason some of you may know, to see room temperature ferromagnetism in p-type samples. So people were looking for acceptor doping. Manganese was supposed to be acceptor. Indeed, manganese is acceptor in this material, but very deep one. So because it's so deep acceptor, we do not see too much carriers at normal temperatures because, of course, this activation is very, very large. So it's very disappointing that actually we do not have any carriers at room temperature, and actually carriers which could be, for instance, oxygen donors or silicon donors are trapped by this manganese, so there's very high resistivity material. And this is actually very interesting for growers of gallium nitride, because for many devices like optical devices or high power amplifiers, you need a substrate which is semi-insulating well. And actually, Martin Zając, who were one of the discoverers that we have this high resistance of material, started to work at Amono company. And Amono company now produces kilograms of gallium nitride with manganese. Maybe in your cars, you have diodes or power amplifiers which use gallium nitride and use this ability of gallium nitride with manganese to be semi-insulating, because this manganese level is very deep in the band gap. So this is a kind of application of this gallium nitride with manganese. But very interested in magnetism during the seminar, and it's controlled gallium manganese nitride. And I'm going to present the work we have done with Darek Stenkiel, Maciek Sawicki, also with Alberta Bonanni group and the Hummel group. Alberta's group beautiful samples and characterized in an advanced way by MOVPE. By contrast, Dietl Hummel and his team was growing samples by MBE, which we have studied. And we have also collaboration with University of Warsaw concerning theoretical description of these materials. So already I mentioned that this gallium nitride with manganese acceptor. It's excellent semi-insulating material. We found that it's up to 10% of manganese. This material does not conduct. And as physics concerns, some of you who has background in high TC superconductors may know that in case of deep acceptors, it's copper. In case of oxygen, in case of superconductors, here we have manganese 2+, which attract holes, and the holes is very strongly bound, and this kind of Zank-Rice polaron physics similar to high TC superconductors. Also, altogether with this hole, this manganese 3+, actually we replace gallium, which is trivalent by manganese, so manganese is 3+, is gallium nitride. And we know also from physics of magnetic impurities, transition metal impurities in various substances like oxide, that in case of non-zero orbital momentum, we have Jahn-Teller distortion, because system lowers energy lowering symmetry if orbital momentum is not zero. And also we have it's Wurtzite structure, so we have trigonal distortion along one cubic axis, because it's by definition a Wurtzite structure. And, this crystal field parameters describing this impurity are now from X-ray, optics, magnetization studies. So we know a lot about this manganese in gallium nitride. And you have here example of magnetization as a function of magnetic field at low temperature. And actually here it's 2% sample, and you can see kind of description of magnetization. You see that easy axis is in plane, perpendicular to C-axis, and this hard axis parallel to C-axis. And this kind of description we can, of course, very nicely describe theoretically, taking out of this tetrahedral field, Jahn-Teller effect, trigonal distortion, spin orbit, Zeeman splitting, and so on. It's kind of standard approach to magnetization in diode magnetic semiconductors. But if we increase manganese concentration, what we start to see it's ferromagnetism. There is some ferromagnetic coupling, and temperature is not very high. You see a few K maybe, but still it is quite interesting what is the origin of this ferromagnetism, mainly gallium manganese nitride. And we can do, knowing a lot about the system, we can do basically with no fitting parameters calculation by tight binding of ferromagnetic exchange. For this charge state, we do calculation of PD hybridization up to first order in this hybridization matrix element. We end up with conclusions that interaction is ferromagnetic. and depends on distance between manganese, like we expect for super exchange, exponentially decay exponentially with distance between magnetic impurities. And how we can plot theory as a function of, and use Monte Carlo. We have been using Monte Carlo to having this interaction energy as a function of distance to calculate TC. Mean field approximation, as you know, does not work in case of short-range interaction. So Monte Carlo has to be used. And well, we can get quite good description. And it's interesting to know for those of you who are interested in ferromagnetic topological isolators, the same mechanism as ferromagnetic superexchange operates, of course, also in this chalcogenides, bismuth, antimony chalcogenides with chromium and vanadium. So this is kind of very interesting and general mechanism of coupling without carriers. And also you can see that it's logarithmic scale, that if you have concentration of manganese above 60%, you cross room temperature. So if you would manage to have locally or macroscopically manganese concentration as high as 0.6 or higher, then you will cross room temperature. So this leads us to conclude, actually, and this conclusion we first got many years ago, and we continue to speak about, that if you observe room temperature ferromagnetic feature in the DMS or in nominally non-magnetic semiconductors or oxide, this results from spinodal decomposition or contamination. So we are very strongly pushing ideas that all this ferromagnetic feature at room temperatures, because you have aggregation of cobalt, or you have aggregation and form cobalt oxide or cobalt metal precipitates, or also you may have, for instance, gallium nitride with manganese, where manganese nitride aggregates with high concentration, and you observe that because you have high concentration of magnetic impurities in diluted system, it is very probable that you have room temperature ferromagnetism. I'm underlying that because each new community, for instance, now 2D layer community, report all the time that they observe room temperature ferromagnetic feature having 2% of magnetic ions. And I'm pretty sure, and actually probably if they make more careful examination of their samples, they will find that they have aggregation of magnetic cations, and because of that, they observe room temperature ferromagnetism. Okay, now we have this random ferromagnet, a random distribution of manganese ions that, again, a very well-known notion for a disordered system, but maybe it's worth to recall in this context is percolation. So imagine that you have this short-range interaction, and then you have ferromagnetic phase transition if you have percolating, if you form a sphere of interactions start to overlap, and you form ferromagnetic cluster. And ferromagnetism in dilute ferromagnetic system was discussed many years ago. And it was noting that if we have this exponential dependence, you can say that if you have temperature T, spins which interaction between them is larger than T, forms this cluster. And from that you can determine how TC could depend on manganese concentration. And this is just percolation theory, which says use that overlapping sphere with concentration N0x, the critical concentration for forming percolation cluster is related that way with concentration of this percolation sphere. So we can we have ideal materials. This gallium manganese nitride is actually ideal material to test this old theory. It's very funny that actually it is not too many dilute ferromagnets to test this theory, because for instance you have metallic dilute system, but in metals this interaction is not exponential, so you cannot test this theory. And we see that more or less we have a very good agreement with this theoretical prediction. Both Monte Carlo simulations and experimental results agree with this old percolation theory concerning TC. Of course, you have to make this time binding calculations. You have to make this time binding calculation to determine this T0 that, but this dependence actually is kind of universal, but you need time binding to scale TC in this particular material. So it's kind of nice test of percolation theory. And I can mention also that we have two other computational developments for Derek Stenke is very active here for determining magnetization as a function of magnetic field. What Derek is doing is calculating quantum levels, not only for single manganese ions, but for pairs, triplets, and complex structure. And in the recent papers in the Journal of Physics, he show how he's successful describing magnetization with this cluster approximation. And also he used another approach, which I think I like very much, is that he used atomistic Landau-Gilbert equation. Some of you know that nowadays people have mean, computational mean, who do not describe macrospin properties, but you can solve this classical equation for individual spins and couple the spin by exchange interaction and see time dependence, time evolution of the system. And the results of this calculation comparing to magnetization are shown here. It was done for almost 10,000 spins. To see this equilibration, you need 280 nanoseconds. And red is simulation, blue are experimental data. And you see that even you can describe this, it's half of hysteresis that you can describe not so badly hysteresis for this easy and hard access in this gallium manganese nitride. So you have a tool to describe interacting system by not macrospin, but also you can use this local spins, but it's classical approach. Okay, so this was kind of where we are now, but now we turn to second part of the talk concerning electrical field effects in this gallium manganese nitride. We are now prepared, we know a lot about the system to understand what is physics of electric field effects in the system. So what we know, of course, from general theory of magnetoelectric effects, that to observe that without external magnetic field, you have to have broken time reversal symmetry and inversion symmetry. And if you if time reversal symmetry is not broken, you need magnetic field to break this time reversal symmetry. And then this is non-zero if this inversion symmetry is broken. Why it is so? It's very easy to see that magnetization is axial vector, electric field is polar vector. So to have this, to transform this polar vector into axial vector, this should be change sign if we change time and if we change R also. So it's very clear to see. And we know that this inversion symmetry is broken in Wurtzite crystals. So actually we have a very nice situation, physical situation to observe this magnetoelectric effects for free because we have from the beginning broken inversion symmetry. And we put this gallium manganese nitride in capacitor structure. We have N-type gallium nitride with silicon as one of the plate of the capacitor. We have gold titanium as another plate. And we look how this gallium manganese nitride magnetism changes as a function of applied voltage, so as a function of electric field. And technically how we do it, we just modulate with some frequency electric field and measure magnetization in phase with this electric field which we apply. We can add, in addition, of course, some additional DC voltage, and then we measure, in a sense, derivative of this dependence on the electric field. And for technical reason, it is good to make many capacitors because, of course, breaking of capacitor, as you perfectly know, somehow increases chance with surface. So if you make many small capacitors, you can eliminate bad capacitors and start on good capacitors. That's a technical issue. We measure dozens of this capacitor at the same time, eliminating this which doesn't work, which shows that capacitance is not as we expect. And okay, as we said, we expect something like that, but if we have paramagnetic material, time reversal symmetry is obeyed and it's not broken. So we should have dependence on the magnetic field, and indeed we see that there is no effect, this magnetization zero induced by electric field in zero magnetic field, but it starts to grow with the field exactly as predicts. We can study as a function of temperature, the effect decays with temperature. Again, here is not magnetization, but electric field induced magnetization. This magnetization which is in phase with electric field which we apply. And also we can study this as a function of electric field, and then this weak field we have this linear dependence as predicted here. So this confirms this linear dependence of weak magnetic fields and confirms this linear dependence as a function of electric field. But the solid line actually are theoretical. I said that we know a lot about the system, so we can calculate just what we expect theoretically with no adjustable parameter. And you can ask the question, what is the main mechanism? What is the mechanism for this magnetoelectric effect? And many of you actually, maybe in the audience, were using a piezoelectric actuator to deform magnetic system to see how magnetization reacts, how magnetic properties changes if you change and apply strain. So this actuator was used to strain our magnetic system. But what is nice about this gallium nitride, it's actually piezoelectric material. So we do not need any actuator. If you apply the electric field to it, it changes. It starts to actually, for positive field here, it starts to grow up and change dimensions. So we just change C-axis, molecular beam epitaxy, substrate and buffer, fixed clamp A-axis, but C-axis can be changed by the applied electric field. And actually, we know that this trigonal anisotropy, this trigonal Hamiltonian and related to it anisotropy depend on the ratio of C-axis to A-axis, and minus something here. Why? Because if actually the C to A is equal to this square root of 8/3, we have just tetrahedral, is regular tetrahedron, and it's all surfaces are identical. But if we apply the electric field, or we can change this ratio. So we can kind of change distance between this nitrogen and manganese in one direction and affect in that way magnetic anisotropy. And this was used in the theoretical calculation, and actually we do not have adjustable parameters because we know this, this piezo, inverse piezo acoustic coefficient, how it changes. Okay, this was paramagnetic gallium manganese nitride. Now we turn to ferromagnetic gallium manganese nitride. We know that increasing manganese concentration, we can make this material ferromagnetic. And you see here again this electric field induced magnetization as a function of magnetic field. These points are red points are experimental. And you see that depending whether we apply magnetic field perpendicular to C-axis or parallel to C-axis, we see different sign actually of this piezo electromagnetic effect. And for your information, the size of this effect is something like 0.3% of saturation magnetization. Okay, so how we can describe this theoretically? And here you have this Landau-Gilbert simulations. I recall you that we do not use any macrospin approximation here. And you see that without adjustable parameters, you can explain actually the sign reversal and the more or less magnitude of the effect. Of course, simulations, so not always some noise simulations, but basically we can understand this effect from this simulation, this kind of shape and this kind of sign of the effect. And to understand this a little bit, what physics is behind this simulation, well, it's not difficult to understand. This is trigonal magnetic field, which comes from trigonal anisotropy as derivative of Hamiltonian over magnetization, contains this magnetization along x-axis, perpendicular to c-axis, along c-axis, and they have different sign. So if you calculate this electric field, use magnetization as a derivative magnetization of the effective field, which consists of external field and anisotropy field, you see from these equations that for one direction and for another one, you have different signs. So this can be understood very well. And also you can see that in high magnetic fields, when this external magnetic field is much larger than the anisotropy field, actually this is derivative of magnetization. And this green points is just derivative of magnetization. So you see that we can more or less describe quite well this effect from the simple theory that here we have derivation of magnetization, which determines the effect. But let's go to weak magnetic fields, what happens in weak magnetic fields. And again, you have here, you see that in weak magnetic fields, you have opposite sign for this electric field-induced magnetization. For hard axis, for easy axis, actually this magnetization has opposite signs that Squid measure, but similar shape as measured by Squid, but in this hard direction, we have similar sign. And the same formula which I showed a second ago can be used, and now we understand that the external magnetic field is 0, this is kind of constant, and indeed we have opposite sign, and we have this proportionality to magnetization. And this proportionality to magnetization is not astonished, because as we said, if we have no magnetic field, like here we have a very small magnetic field, this should be change sign under time reversal, and therefore time reversal is broken here by the non-zero magnetization. So in first linear approximation, this should be linear in magnetization, as we see here from this formula, and of course expect from this general magnetoelectric effect. So it's kind of well understood and simple theory which can explain our observation of electric field effects in this gallium manganese nitride. And it is interesting that if you switch now, in addition to this AC magnetic electric field of small magnitude, relatively small magnitude, we add large magnitude of DC electric fields. Not too much happens, actually. We see that this, this curves looks very similarly, so there's not too much effect of background additional electric field, which suggests that we have linear dependence on electric field, and derivative, which we measure by AC, by applying AC electric field, is constant. So effect is linear in electric field as expected from this formula. But yeah, this, so far we understand everything. It's nice, but we have some effects which we do not understand very well, and the effect is shown here. Namely, I showed that we switch a large electric field and nothing happens, special happen. But now we have we do different experiment. We measure this response to an AC electric field, and we get what we got before. It's a little extended scale, and we now being here. Remember, hysteresis go like that. We measure in that direction, yeah. So we measure like that. So now we come back from high magnetic fields, and we are on positive side. We started from positive side and stop at the positive side of the magnetic field. And now we switch large DC field, and nothing happens. Actually, nothing happens. This derivative which we measured is shown here by these orange points, and nothing special happens, which confirm what we said before. But situation differs if we go to negative magnetic field. Now in this point, we start to switch on additional DC electric field. Yeah, we see that this response changes sign even. We switch magnetization, sign of magnetization. So switching, introducing magnetic electric field here, we kind of move towards equilibrium states. Yeah? Magnetization wants to be directed along the negative magnetic field. And we can do another experiment. We can look for coercive fields in AC, large AC electric field. Now we put large AC electric field. Here I recall we get small electric field, and we edit DC field. Now we switch on a large, we measure the function of large AC field, and we see that coercive field, this coercive field decreases with its electric field, independently of actual frequency which we use. So we have narrowing of hysteresis, which is used by this AC field. So it's kind of interesting effect. And how to explain it? One of the explanation would be that we have just heating, because what we do, we charge capacitors, capacitor here, we charge capacitor here, and heating could just bring our system to thermal equilibrium when we cool down afterwards. So one of the possibilities here, heating by capacitor charging. But actually, in 1 week, on Tuesday, during jam session, Derek Schwenkel will try to convince you that we see precessional switching. That it's not heating, but we observe precessional switching induced by this trigonal, additional trigonal field, which we introduce here. Okay, this was samples without any any carriers, and it was in dilute magnetic isolators, but we all know that there are many materials in which we have holes, and these holes mediate ferromagnetic RKKY kind of interaction, mediate ferromagnetic coupling between manganese localized spins. And these holes can originate from manganese itself. Manganese can be acceptor, shallow acceptor, some materials, as we said, gallium manganese nitride is deep acceptor, but in many materials, it's shallow acceptor, doped material with holes. These holes can be introduced by acceptor impurities in the cases when manganese impurity is neutral, is divalent, replacing divalent cadmium, or these holes could be due to defects in many materials, like 4,6s, for instance, vacancies introduce a lot of holes, and these holes introduced by defects can mediate ferromagnetic coupling with various temperatures. And again, the question arises, what happens if we apply electric field to such a system? And as you know, there are a lot of papers, a lot of beautiful works done in Tohoku, other places, on this magnetization changes induced by gating. So now we have structure that ferromagnetic semiconductor is conducting. It's a plate of the capacitor. Another plate is again metal, and we put oxide insulator here and other insulators, and we have capacitor structure, field effect transistor structure if you prefer. And of course, we know from years that in such structure we have to use Poisson equation to describe distribution of magnetization inside semiconductors. And now interesting question arises, which also concerns multilayers, interface, and junction when we have inhomogeneous or non-uniform carrier distribution. How to describe TC in such inhomogeneous system? Yeah? TC depends on the carrier density. It's mediated by holes. So question arises how to describe whether maximum of TC or minimum of TC determines TC in such inhomogeneous system. And I think new interesting concept here is to realize that what counts is phase coherence length. That actually phase coherence length determines length scale at which TC should be averaged off to obtain the TC which is observed experimentally. And such theory was developed some time ago, and actually formula for this overaging on TC, getting TC, macroscopic TC, which is in homogeneous system, but on dimensions smaller than phase coherence length is given here. Well, if you think a while, you can imagine how to get this formula, but important physics behind, which you should always remember in case of inhomogeneous system. that it's not maximum TC, not minimum TC, but some kind of collective states. It's a kind of collective sample quantum mechanics, as you know, is non-local, and TC is determined collectively by this kind of overaging procedure, which take into account this non-locality of quantum mechanics. So here it's just TC, measure TC as a function of Hall concentration, total Hall concentration, which is changed by gate voltage. And if you forget about what I said about this non-locality of quantum mechanics, you get something like that. But if you properly take into account this non-uniform distribution, you can obtain quite good agreement with experimental results. So now, as the next effect, just to change a gear. Many of us are nowadays very much interested in antiferromagnetic spintronics. And you can ask the question about gating of this material. So I will show just very simple results concerning field effect in copper manganese arsenide, very famous antiferromagnetic material used for spintronics. And what was done here, what Michał have done here, he put ionic liquid on this thin layer of copper manganese arsenide, prepared gate, and measured how resistance of this material changes as a function of gate voltage. So what he was measuring is field effect, what we call field effect, how resistance changes. Of course, these changes of resistance, which you expect, are not very large because it's semi-metal. So you can you change carrier density, but of course you have background, very large background density. It's semi-metal, is not semiconductor. And he managed this change of resistance of the level of 0.1%. And he managed to measure this change of resistance, from which he was able to determine the field effect mobility. Now, probably some of you who are familiar with semiconductor physics, it's kind of standard that measuring of field effect in materials, you can determine mobility. And in this whole structure, he was able to compare this field effect mobility with this Hall mobility, and found actually very good agreement that Hall mobility measured by Hall effect is very similar within experimental error equal to this field mobility. And he was able to draw several conclusions from that. Namely, that this agreement suggests that if multi-carrier transport is present here, it's not very important actually, because otherwise you would not get this agreement. Also, anomalous Hall effect induced by field must be small because this would affect Hall mobility. And also that there is no electrochemical interfacial reaction, that this change of resistivity is not due to electrochemistry, but due to change of carrier density. So this brings me to end of my talk. Just to summarize, I have introduced several concepts, or recalled you several concepts in dilute magnetic materials, spinodal decomposition, which lead to self-organization and may lead to high TC ferromagnetism in some cases. Also, anisotropic spinodal decomposition is a very interesting effect, which leads to pneumaticity in many systems. I contrasted antiferromagnetic superexchange with ferromagnetic superexchange, saying that this leads to frustration and spinless freezing, but here we have percolation, a very nice test of percolation theory. Also, I discuss electric field effects in dilute ferromagnetic insulator and dilute ferromagnetic type semiconductors, saying that here we have piezoelectromagnetic effects dominating, that changing by converse piezoelectric effects, changing dimension of the samples under electric field effect, magnetic anisotropy. And here I discuss gating effects, in particular TC, in electrically non-uniform system. Thank you very much for your attention.
Thank you very much, Tomasz. So I would like maybe now some questions to maybe Burkhard, do you have a question first?
Yes, I do. Thank you very much, Tomasz, for the very nice overview. You know, I'm not from the field, so for me it's always very interesting to see what happens in the field. The question which was arising is, what is the future about this diluted magnetic semiconductors? I hear a lot that they are discussed as good or excellent model systems for this new topological applications. How would you see that? Would it make sense to invest at the moment into this material class, or is it over and we only have to finish up with some very nice remaining effects? How would you evaluate it?
Thank you for the question. Of course, I was historic, but I could be less historic. But I wanted, as you just mentioned, just make overview a little provoked by the fact that I had to write this chapter. But I would say, if you think about quantum anomalous Hall effect of axion insulator, you see that the future or presence of this dilute magnetic semiconductors is very bright. Yeah, main topologically, I think the most interesting topological effects are discovered in magnetically doped topological insulators. As you remember history, people at the beginning believed that there is kind of contradiction between magnetism and topologies, that healing time reverses symmetry by adding magnetism will produce, take away topological effects. Actually, what we see is opposite, that if we dope the system with magnetism, we see much more interesting effects that without its magnetic impurities. And two examples, which I just said, is quantum anomalous Hall effect, which may have relevance in metrology. It could provide Hall resistor standard without any external magnetic field, just to ferromagnetism. Time reversal symmetry would be broken not by magnetic field, by magnetization. And this axion insulator predicted a long time ago by Bicek, it's actually proven or close to proven in case of this dilute ferromagnetic topological materials. So these two examples show that this magnetic doping is kind of root in any material. And now in 2D system, also people, I mentioned a little, that in 2-dimensional layers, people also adopt magnetically, and for sure they will see many interesting new effects, I'm pretty sure.
Yeah, let me ask Igor Masin. Igor, go ahead and ask your question. I think, does he have the Igor? Did I allow you to? Oh, sorry. Did I? There you go. Sorry, Igor, go ahead.
Okay, now I was.
Sorry, I clicked the wrong person.
Well, as a matter of fact, it's probably not that important because my question was just technical question to an earlier part of the talk. I was a bit surprised to see manganese 3+ in tetrahedral nitrogen environment to acquire orbital moment of 2, because in tetrahedral environments, 3+ should have one hole in the T2G band, which can have maximum L1. To get L2, you have to mix EG and T2G, and how manganese managed to overcome this huge crystal field?
Oh, I think in tetrahedral environment, it's quite okay. You have T, G, two electrons, if you prefer, on TG states and 2 in EG state, and you have orbital momentum 2. Actually, for it's I would say it's not surprise.
No, I'm sorry, EG is fully occupied. Tetrahedral is reversed. EG is fully occupied.
TG is 2 electrons sit on.
Yeah, so EG is fully occupied, and then and then you have right, and then you have one hole in T2G.
Yeah,
and this hole somehow manages to get L2.
No, but you get from this 4 you can think that you have 4 electrons on this shell, and you can very easily manage to have this L.
Yes, if you don't have crystal field, but so somehow the crystal field should be very weak here, and I'm surprised that it is, because it looks like. Well, anyway, that's it. I think it's highly unusual, but anyway, maybe another semi-technical question is that you keep talking about ferromagnetic super exchange on long distance. But mechanisms that I know about of ferromagnetic superexchange, like Goodenough Kanamori or T2G exchange, they all work only for nearest neighbors. Everything long range should be double exchange, not super exchange. What is the actual mechanism for ferromagnetic superexchange at such long distance,
So
which is
you're
distinct from
perfectly
double
right.
exchange? Huh?
You are perfectly right. It's a short range in a sense that it decay exponentially with the distance. So you're perfectly, it's a kind of no contradiction. It's just what are you saying, that it decay very strongly with distance exponentially, but still you have its exponential function decay very fast.
No, short range, I mean nearest neighbor specifically.
No, you have next, you can calculate by time binding, as I said. It's just standard calculation by time binding. And if you do that by time binding, you here you see exponentials.
Yes, and that
scale.
would be double exchange that you, because you do time
no,
binding
you just
calculations.
calculate. Well, it's maybe a matter of definition, but
maybe it's a matter of definition.
You can go to our paper on that, and we just calculate super exchange as a function of distance. And you're perfectly right, it decays very fast, but it's still...
No, but what you call super exchange is basically full total energy that comes out from tight bonding. You're not trying to separate it into super exchange defined by Anderson and Kanamori. You call everything super exchange.
And interesting thing is that you know here from XAS, from photoemission spectroscopy, you know parameters which determines these integrals, and there's no mysteries here. You just calculate. And here, by the way, you have these 2 electrons here and 2 electrons here.
That's the point. Yeah, that's okay. All right. Anyway, thank you.
Okay, let me pass it over next to Igor Rosansky.
Yes, thank you. It's a practical question. So if I consider the exchange interaction constant, which describes the interaction of conductance band electrons with manganese in gallium manganese nitride paramagnetic, how would you compare this constant with the gallium arsenide with manganese? And the same question for the holes, for the PD.
Mm-hmm. Mm-hmm. So for the holes, actually, we know, as I said, we know this from photoemission and XAS. We see how this hole interact with manganese, and we can determine. And we know that this parameter, it's larger compared to other material because, of course, it scales with distance, and here distances are very small. Yeah, in case of gallium nitride, lattice constant is very small. So you have a little larger beta, if you know what I mean by beta, this PD exchange integral. It's relatively large in gallium manganese nitride. In case of electrons, it's a very interesting situation. Actually, there is a paper by Schlieva and myself where we discuss this behavior of electrons exchange integral. And here we should consider of course, many effects, including that this contrary to 2,6 materials where manganese is neutral, here manganese is charged. So somehow this should be taken into account, that manganese is charged in n-type samples, and this affects the distribution of electrons around manganese and affects this alpha. And generally, this alpha, this SD exchange integral in the 3/5 is smaller than the 2/6 because of this electrostatic effects. And I refer, and probably you can consult Schlieva and my paper about them from 2011 when we discuss exactly this question you have been asking.
Thank you so much.
Yeah. Yes, you had a question?
Yeah, so thanks, Tomasz. Very nice talk. Could you just go back to the slide with the copper manganese arsenide, the electric field gating?
Manganese nitride, yeah?
The copper manganese, was it copper manganese nitride, the electric field gating?
Yeah, it's paramagnetic, and here's
paramagnetic. No, the one with the copper manganese arsenide, I think. Yeah. Where you had the 2 nanometers of aluminum on top. Just a little bit before, it says copper manganese arsenide with electric field, where you have the 2.
Sorry, this antiferromagnetic, sorry.
Yeah, exactly.
Yeah. Mm-hmm.
Yes. So 2 questions. So you gate through the aluminum oxide, is this correct? Or you gate from below?
Yeah, we protect material by aluminum oxide. And then we use ionic liquid, yeah, to protect material from chemical reaction with liquid. We use oxidized aluminum. Yeah.
So the question is that, I mean,
we use ionic liquid to produce electric field, but we protect our copper manganese arsenide by oxidized aluminum.
And I wonder how much really it is oxidized through, because aluminum, 2.5 nanometer aluminum usually doesn't oxidize all the way through it. Aluminum is very conductive. So I'm just wondering if the effect in reality is much larger and you just get a lot of screening from unoxidized aluminum at the interface between the copper manganese arsenide and aluminum.
So we hope that not, that we check this. That we oxidize properly, but thank you. We have maybe checked more carefully. Thank you for this remark. We thought that we somehow did this properly, but we have maybe checked after your remarks that oxidation was not full. But let's say we used silicon just to probe capacitance and kind of play with whether we control capacitance of the system. And we had impressions that on silicon, we understand capacitance quite well and we control the system, but maybe we should be more careful. Yeah?
Okay. And would you expect theoretically that copper manganese antimony has a similar effect?
I would say that yes, but question is, we change resistance. So it's very important what is background resistance. Is background resistance very small? Of course, it's very hard to see the effect, yeah? This just, there are no secret here, simply that you take equation for capacitance and you induce certain concentration of charge, and if this concentration of charge induced by capacitance small comparing to a background, you see nothing, yeah? Or see something very small.
It would be at lower temperature because the ordering temperature of the copper manganese.
Yeah, we did everything at room temperature, and this, of course, issue ionic liquid is very nice capacitor. You can get a very large.
Yeah, but only when it's liquid.
Yeah, but by definition, and people cool down. It's very tedious because you have to, if you want to change voltage, you have to heat up again and so on.
Yeah, I understand.
But it perfectly works at room temperature. Is not so good for lower temperature.
Okay, thanks.
Gisela?
Yes, can you hear me?
Yeah.
And thanks for this impressive overview. This brings me to the question to an expert. You showed in your talk that you have a lot of, you have to be aware of a lot of defects, irregularities, inhomogeneities. How reproducible are the results? If you look in your own lab from sample to sample, and then from different groups and so on, how reliable is on this basis really the parameters or the physics you want to get out?
Yeah, so thank you, Gisela. Of course, it's a very relevant question. So if you go to gallium, for instance, this gallium arsenide, gallium manganese arsenide, I think people managed to get reproducibility. Yeah, it required a lot of effort. Jairo was also involved in this effort, how to make material by annealing reproducible, how to avoid also aggregation of manganese. Hideo was very instrumental to show that low temperature Mb produces this random distribution. In case of gallium manganese nitride, a similar story. That in the case of gallium manganese nitride, a huge effort, and I maybe underlined that at the beginning, that you need huge advanced characterization here to really be sure what is going on. And we used also methods you specialize in. We use a lot of synchrotron radiation method. We use a microscopy. And it would be very interesting history how people managed to control this gallium manganese nitride and how many years it was required to finally control this material to have random distribution. And I said that this percolation theory confirmation demonstrate indirectly that we have a really ideal random distribution. And both these groups really spent huge amount of time to characterize this material. But it was a long story actually with gallium manganese nitride and also gallium manganese arsenide to arrive to reproducibility.
Thanks.
I have a small question. So I guess in the copper manganese arsenide at the end, you said that you were trying to measure animal Hall effect?
No, what I wanted to say that a priori, a priori, what you expect in antiferromagnetic materials, that you may have difficulties with distinguishing between anomalous Hall effect and normal Hall effect, because both are linear in the magnetic field. In ferromagnet, it's kind of easy because one depends on magnetization and other on external magnetic field, and you can kind of try to manage to distinguish between the two. Imagine that for a reason, one another reason, you have huge anomalous Hall effect in copper manganese arsenide, then you will have linear dependence on the magnetic field of it, because magnetization is linear in the magnetic field. Yeah. And then your determination of Hall density will be wrong, because you will have linear slope due to anomalous Hall effect and not due to normal Hall effect. So I wanted to say that this agreement between these two,
you're assuming from the canted magnetic field from canting.
Yeah.
Because otherwise, it's not normal Hall effect expected, because I mean you can have anomalous Hall effect in an antiferromagnet collinear, but not in this one, because this one has crystallizes in a system where you have the lattice coupled by a translation operation, which necessarily gives you an effective time reversal symmetry, which kills anomalous Hall effect. But others you can. So I'm glad you don't observe it. Otherwise, it would be bad.
Yeah, but exactly good points that you may, and this is the case of this crystal Hall effect you introduced, yeah, this notion you introduced, that you may have very small magnetization due to small canting, but actually huge anomalous Hall effect, yeah.
Not in this case. In the case of copper manganese arsenide, would only
not the case,
from what you say, from the canting. Otherwise, it would be zero. It would not be allowed by symmetry. It's once you put the magnetic field, of course, you break that symmetry.
I want to say that this crystal Hall effect is very nice, because it shows that orbital magnetization counts, not spin magnetization, but orbital magnetization is determining anomalous Hall effect. And this is a beautiful example for that. Yeah. But you're right, of course. But I said a priori, let's say that we do not know anything, and we just worry that our Hall effect measurements can be affected by anomalous Hall effect. Right. And then field effect can tell us to what extent.
Okay, I understand the point now. Okay, great. Well, I think that's all the questions so far. So I would like to thank you once again for a wonderful talk, and everybody, the 150 people or so that 160 or so that showed up. And next week we have actually Karen Eversosite giving a talk. I have to put it up on the website. And after that, we'll take a break for a month or so until we came back on January. So welcome, everybody. Thank you, everybody. And stay safe and stay negative. Negatively tested. And yeah. So thanks again, Tomasz. I'll stop now.
Thank you very much. Thank you for questions and thank you for being. Bye-bye.
Okay, thank you.
Thank you very much. Bye-bye.
Thank you for joining us. Thank you.